Yeah, hi, I'm James. I'm here to talk to you about breaking changes. To provide a bit of context and introduce myself, I am the creator and maintainer of, among other things, this set of NPM packages that provide WebSocket messaging, like various layers of that protocol. They're quite widely used by a lot of different projects. They generate about 8 million downloads a week between them. And I've been maintaining these pretty much since Node was released, so since early 2010. So this is a reflection on my experience as an open source maintainer of seeing things change over time and what the effects of that are. Additional bit of context, this talk should not be construed as a complaint about how things work. We should be really grateful for all the software that we get for free that lets us do loads of amazing stuff. I'm more trying to reflect on, again, my own experience rather than bashing anybody else and saying you're doing this wrong. It's more like how can we reflect and improve what we're doing. OK, so with that out of the way, what do we mean by breaking? Well, consider this module at the top that has a method called get, and it takes a URL, and it makes an HTTP request to that URL, and then it invokes your callback with an object containing the status code, which I've hard-coded here as a number. Now, let's say that we change that number, 404, and replace it with the string 404. Do we think that's a breaking change or not? Well, to answer that, we have to look at some use cases. So if something's calling this function, and it's using the weak equality operator to compare the numbers, that will keep working, because in JavaScript, a number is weakly equal to its string representation. However, if we're using strict equality, this code will now break, because numbers and strings are never strictly equal to each other. So if we have this code, we consider the change to the HTTP module to have broken our program. Here's another example. This module contains a method that takes the name of a table, and it runs a query to count the number of records in that table. And then it invokes your callback with the count, which, again, I've hard-coded. Now, notice something about this module. This is structurally identical to the other module that I just showed you. All I've done is replace some of the names. The actual programmatic structure, in terms of what the compiler cares about, is exactly the same as the HTTP module. So if we believe that breaking changes and compatibility is purely a function of the source code itself, then we have to give the same answer for the HTTP module and this one. So let's look at some use cases. So say somebody is counting the number of records in two tables and then subtracting them, for example, to work out the number of remaining tickets left for a conference. Now, in JavaScript, the subtraction operator coerces strings to numbers, so then you get arithmetic subtraction, and you still get the same result as you were getting before. But if you're adding the two counts together, JavaScript's plus operator has an overloaded meaning. It performs arithmetic addition of numbers, but it also concatenates strings together. So if something that was previously a number is now a string, we get the string concatenation of those two values. So this program no longer does the same thing, and the author of this program would consider it broken by the change that we've made. So yeah, we would have to make an explicit change here to account for the fact that the database module has changed how it represents the results to us by explicitly converting the strings back to numbers again. So what we've seen here is that the meaning of values in programs is not fully contained within themselves. And it's not to do with just what their type is. A number can be used for several different purposes. It depends how you're using it that determines whether changing it would be a problem. And so what we've seen is that rather than just being a number, something having one type, it actually has a set of characteristic traits. A Java programmer might call these interfaces. Haskell users might call them type classes. But the core idea is that a value of a certain type can be used for several different kinds of operations. And it's which of those operations that you're using that determine its true meaning. So we've seen a couple of these already. A number might be used for its identity. An HTTP status code is not really an arithmetic number. It's just a machine-readable label for something. But numbers also have arithmetic properties. You might want to do maths with them, addition and subtraction, and so on. So that's a little bit of an examination of the complexity that even exists in very simple values like numbers. What about objects? What happens when we change the interfaces to those? So let's say we have a function that returns an object that contains some information about a talk at a conference. In fact, this talk at this conference. It contains a title, a date, and a presenter, all of which are strings. Now, adding a new field to this object is probably not a problem. Any program that's using this will probably just ignore the fact that the new field exists, right? It won't be relying on it, so this object gaining a new field won't disrupt any existing code. However, if we remove a field, like the title object, sorry, the title property, some code that's using this function will now probably break. So for example, if we're calling getTalkInfo and then putting the title attribute of the result into a string, we'll now get a string containing undefined. And this is a case where JavaScript doesn't alert you to the fact that it's made a mistake. You don't get an error if you access an attribute that doesn't exist. You just get the value undefined, and that shows up in the string. So the program is not broken in the sense that it's crashing, but it is clearly not doing what was intended. A user will notice that something weird has happened here. Likewise, changing the types of existing fields is likely to break existing programs. So for example, if we were calling getTalkInfo and then splitting the date field on dashes to break the date into its component parts, that will no longer work because a date object doesn't have a split method. So in broad terms, adding new fields to an object is fine. The existing callers will just ignore that new field. Removing a field might break things, as we've seen, and JavaScript won't alert you to that problem. And changing the type of existing fields can also break things. And sometimes you'll get an error because you're using a method that doesn't exist, but sometimes the program will silently do the wrong thing. But it's not quite as simple as that. JavaScript, being a small language, has overloaded the few abstractions that it has with several different meanings. There are multiple different ideas in computation that are overloaded onto the same thing in JavaScript. And one of those things is object. We use objects to represent the computational idea of maps, of records, of object-oriented programming style objects, and several other things. So what do these terms mean? Like, we're using this one thing object for a lot of different functions. We need to think about like the different ways in which it's used. So a map is an open-ended collection of key-value pairs, and typically the program doesn't care about what specific keys are in the object. It's just data, and it gets processed, like whatever that is there gets processed. So typically, if your program is just iterating over an object and processing whatever it contains, you're using the object as a map. A record is a value with a fixed set of known fields where the fields can have different types, and the program usually cares about specific fields within an object. So the props you pass to a React component are a good example of this. You don't just iterate over them and do the same thing with all the fields. You'll usually pick out specific fields and put them in specific places in your UI. An object-oriented programming kind of object is a bit like an extension of a record. It's a computational value that combines state with behavior. So it's like a record where some of the fields are functions that access the record's other data fields. So the image value that I used in the previous example here is a good example of that image.url bit. Comes from a class that takes a name, and it has a method that knows how to calculate the URL for a particular size of an image. Now, typically, adding new methods to an OOP-style object is fine. That's what enables polymorphism. That's what means that one function can work with lots of different kinds of objects as long as they all have a method in common. Iterables in JavaScript is a good example of that, and that's where a lot of the power of OOP comes from. But adding new fields to other kinds of things like records can cause problems. So for example, if you add a field to your Webpack config that Webpack doesn't recognize, you'll get an error. It doesn't ignore this key that it doesn't know. It actually checks everything your object includes, and if it doesn't recognize any of it, you get an error. And it's doing that because in the kind of program that Webpack is, it usually indicates an error on the part of the user if it includes data that shouldn't be there. It usually indicates a typo or a field that's no longer supported if you've upgraded from 3 to 4. So it's not always the case that adding new fields to something keeps your program working. In some cases, it will break them, and that's done for ergonomic reasons to help the user use the program correctly. Likewise, if you're inserting something into a database, if you try and save an object to a table, and that table doesn't have a column for one of the properties your object has, like, what should you do? Should that be silently ignored? who's to say? So like ORMs typically include explicit instructions for like these properties get saved to the database and these ones don't, and the user has to decide like which things belong in which category. So that's a little bit about like we've seen how primitive values like numbers can be contain quite a lot of complexity, and likewise something like object can take on a lot of different computational meanings, and so changing it has different effects in different circumstances. But another thing that causes programs to break is that just the concepts we're expressing are too complicated. So one example of this was the recent proposal to add the flatten method to the array prototype. And a lot of people petitioned TC39 to not do this because it would conflict with another implementation that was already out in the wild. But why would this be a problem? Well, it's partly for sort of logistical reasons. Like TC39 is responsible for the environment that exists in the browser, right? So we as developers don't have control over that. Our code gets deployed into all these browsers, and it just has to deal with whatever's there, right? It's not like one of our dependencies where we get to choose which version it is. Anything that's in the browser affects how our code runs, and we don't have direct control over it. So TC39 changing things in a way that conflicts with our code can cause problems. But why does that conflict even exist in the first place, right? If we were talking about a fairly simple function, it's quite likely that TC39's definition would agree with the one the community had already adopted, and we wouldn't have a problem. But the thing with the flatten method is that it's extremely conceptually complicated. Here's one potential implementation of it. So we implement flatten by reducing, starting with an empty list, and concating all the elements of the array together. And the way the concat method works means that this will essentially combine any nested arrays inside the outer array and flatten the array to one level deep. But you might decide you want your array flattened infinitely deep, and this won't do that. Or you might care about other kinds of collections, so like other iterable values like string. Should they be flattened? What about if your array contains a set that contains an element that's already present in the outer array? What's the effect of null? What does it mean to even combine all these values? There's a very broad set of decisions to be made here about what this function even means. And that means that there's a very broad space of different implementations of it. So if you put two implementations of this function in the same program, they're likely to disagree with each other. And so one way that you can avoid breaking things is to avoid using functions that are this complicated. Often if you have something and you want to flatten it to one level deep, you probably want to use flatmap instead. If you know your data structure is nested arbitrarily deep, you might want to use the visitor pattern or an interpreter. If you don't know how deeply nested your data structure is, then you actually have a deeper design problem that needs fixing. So there's a lot of complexity inherent in this method that means that it's just hard to make it interoperate. We saw a similar thing with the buffer constructor in Node. So that was taking several different types of values and giving different behavior depending on the type. And it was really easy to pass a number instead of a string and then get different behavior. And this caused security errors in some WebSocket implementations where you could make the server expose unsanitized memory to you. So we fixed that by turning it into several different methods that made it explicit, like the user would make it explicit what behavior they wanted. Either they want a buffer that contains the byte data for a string, or they want a buffer that is a fixed size of memory. And now you've made it unambiguous. The user is saying what they want. So it's not just about the return values that our programs have and how things are consuming them. There's also an implicit contract between any function and the things it takes in terms of what properties it expects them to have. So take this contains function. This takes a list and a value, and it returns a count of the number of times that value appears in the list. It does that by initializing a counter to 0, and then using a for of loop to iterate over the list and incrementing the counter. This works fine with arrays, as you'd expect, but because it uses a for of loop, it also works with any other kind of iterable value. So somebody's currently using this with a set. It will only return 0 or 1 for a set, because sets only contain one instance of each value, but that's good enough to retain truthiness, to detect whether something exists in the set or not. So now, say that the author of the contains function decides to change it. Their assumption is that it's only being used with arrays. So they'll use array methods to change how it works. They'll now implement it using the filter method to filter for values equal to the input, and then return the length of the result. So this continues to work with arrays just fine. But now it blows up when you give it a set, because sets don't implement the filter method. We get a slightly unobvious error here, like the word filter doesn't correspond to anything the user has said here. It's actually an error being thrown by the internals. But the program is now rejecting an input that it previously accepted. And that's because the author assumed that people would only use it with one kind of value, but they never made that explicit. So we should also consider side effects when looking at our programs. So JavaScript being an imperative language, our programs don't just call functions and return values, they also have side effects. So for example, here's a function that adds a dependency to a package.json by reading the file, parsing it, adding the dependency, and then writing it back to disk. If we add a console.log line at the end of that to just log what's happened, is that a breaking change? Well, it depends where it's being used. If it's embedded inside a program that is expected to produce JSON output and pipe that into something else that processes it, adding this log line will make that program fail. Likewise, if you have an event emitter, you might decide to add a new value to the data that is emitted with an event. And JavaScript lets you call functions with more arguments than they were expecting, so this ought to be fine, right? But turns out somebody's using a variadic function to listen to that and expects all the values emitted to be of the same type and be processed in the same way. So I could go on with these sorts of examples all day, but the core theme here is that JavaScript doesn't make it particularly easy for you to write code that works today and keeps working. It's very permissive. It will often run code that you would expect should throw an error. When it does give you an error message, it's often kind of unhelpful and doesn't really identify which bit of the program is incorrect. And it has no way of you telling the compiler how you expect people to use your program, so the compiler can't tell you if you've changed something that would break those expectations. Right, so enough complaining. What can we actually do about any of these things? So one popular answer to this problem is semantic versioning, or SemVer for short, which is that you format your version numbers as three separate numbers, where incrementing the first one means that you've made a backwards incompatible change. Changing the second one means that you've added a new feature in a backwards compatible way, and changing the last number means that you've made a bug fix. But as we've seen, compatibility doesn't just hinge on the module itself. It hinges on the context in which the module is being used. So SemVer has some conceptual limitations in that sense, but also some practical ones. It's quite hard to express fine-grained information. Like, you might have released a breaking change, but you haven't, all the functions that I happen to be using from your package are still fine. So I can't tell just from the version number whether it's safe to upgrade. And you can see this playing out in the ecosystem in that a lot of the times when I've seen breaking changes in production, they actually show up in bug fix releases. So one example of this was last year we had a denial of service vulnerability in per message deflate. And the way this played out was that at the end of 2016, the zlib library released version 1.2.9, which is its first release in 3 years, which gives you some idea of the resources available to maintain something easily as widely adopted as zlib. And that contained a change that meant previously valid configuration values that are required by the WebSocket compression protocol were now illegal, and it would throw errors on them. In April the following year, Node.js released 4.8.2 and 6.10.2, which bundled this version of zlib and began breaking WebSocket servers. In August, when we were preparing a new release of the libraries that I maintain, we discovered this issue, reported it to the Node project, and Miles from the Node project reported this issue to zlib, where it remains open. This is not necessarily a bug in zlib. This is very much up for debate. It's zlib's intention that these values are not legal and you shouldn't use them. But they didn't know that this would break stuff to do with the WebSocket protocol. So a month later, after we'd spent time figuring out all the possible solutions, the fact that we'd have to deviate from the spec to make the program stop crashing and written everything up, per message deflate released a patch. And then a month after that, Node.js released versions 4, 6, and 8 that made a patch to their zlib bindings that sort of paper over the problem. So this gives you some idea of the time it takes for these changes to propagate through the system. Everyone's working with imperfect information, and we have to figure out what's going on, and that takes time. So when you're changing a system, you don't just have to look at the meaning of the program on its own. You have to think about the effect on the ecosystem of the community for the information in that change to spread. If you make too much change too quickly, you end up leaving everybody behind, and people don't end up upgrading your software. So another approach to dealing with breaking change is to just try and never break anything, right? Which sounds like a pretty extreme position, and I'm not sure any of us would ever manage to quite live by this standard. But it is a constraint that people try and live to. Like we saw Ryan yesterday say, it's my fault and I'm very sorry. Unfortunately, it's impossible to undo now. This is like the world that we live in. Like too much stuff depends on our code and we can't change it. But it is what I try to live by in my software, and that's partly to do with the logistics of how maintenance works. So there's two main reasons why I try to work this way. So the first is that I'm not in direct contact with all of my users. If I want to change something, it's very hard for me to inform the large set of people that are using this code that I'm going to change it and they might need to update something. Also, most of the people that are running my code don't even know that they're doing so. My modules are typically embedded as transitive dependencies inside other things that people are using. So there's 2 or 3 or 4 levels of intermediaries between the end user and my code. So if I break something, there are several other authors and projects that would have to paper over that for the end user to see any benefit from it. But the other thing is that because I do open source in my spare time, I don't have a sort of predictable amount of bandwidth for fixing problems. So it's much more valuable to me to try and keep things stable rather than to take the risk of releasing stuff that might break things and then have no visibility in when I might be able to deal with that later. So I take a similar approach to my dependencies. Like I typically leave them open-ended rather than pinning them with the caret or the tilde operator, because I want users to have the same thing. I don't want me to be a bottleneck on people being able to get upgrades of the things that I'm depending on. And I am taking a risk here that these things might not be stable, but that's countered by other measures. Like I'm quite conservative with the things that I depend on. I'll typically try and adopt something and then live with it for a few months to sort of see how it pans out, and I get an understanding of how it evolves over time before I release it to my users. So all this hinges on communication. All of this stuff is, we've seen a lot of talks at this conference about how we communicate with each other. The core message that I want you to take away from this is that compatibility isn't a sort of objective, technocratic thing about the code itself. It's about the fact that we all have imperfect information about the author and the user and the software know different things about the software, and that means that the author's intent and the user's usage will deviate. So the best ways that we can try to avoid things breaking is by affecting how people use our software and how we communicate with them. We can partly do that through the code that we write. So JavaScript is still a small language, but it's grown a few things recently that help you express yourself a little bit better. It might be more appropriate, rather than using a plain array, to use a set. That might help you be more specific about your meaning. Instead of using a plain old object, it might be more appropriate to use a map for the distinctions that we saw earlier. If you want to think about the operators and functions that you're using, if you know you're doing string concatenation, then rather than using the plus operator, which is ambiguous, consider using templates or the join method that tell people that you know you're doing string concatenation. You can try and avoid brittle idioms in the language that make it likely you'll have to change your mind later. So for example, if a program is growing a long list of parameters and you keep adding more things to it, that makes the callers to those functions a bit cryptic. Like, what do true and false and zero mean? I don't really know. And it also, every time you add a new parameter, it gets more complicated. A nicer way to do this might be to use object destructuring and therefore sort of simulating named arguments, and you can easily give them default values. That makes the function easier to change, and it also makes the caller clearer about what it's doing. A really good example of this is callbacks. So if you want to add a new parameter to a callback function, that parameter needs to go before the callback, and then you need to do some sort of mending up at the top of your method to account for callers that aren't passing that new parameter yet. It's much easier to do this if your function returns a promise, because the parameter list hasn't been polluted by this extra parameter that needs to be at the end. So it's much easier to just add a new parameter there with a default value and not have to add any of that extra stuff. Think about your error design. Errors should be a way to help users write code that works. They shouldn't be a scary thing. They should be there to help people. Things throwing errors when you're making a mistake is good for you. So for example, rather than that cryptic error that we saw later about filter not existing when we passed in a set, we could put an assertion at the top of our method that checks, oh, I expect this to be used with an array. If you're not passing an array, I'll give you a method that tells you that's what I expected. So you can spot the bug in this code. It's probably not very obvious. So the bug is that bytes has to be an integer, but not all numbers are divisible by 8. So sometimes we'll pass a fractional value here. This code worked fine until node 9. It actually, like the crypto library, rounded the number down. But the program that was using this, it didn't matter too much because it was actually asking for a lot more random data than it really needed, so the number being rounded down slightly wasn't a problem. But then in node 10, we started getting an error, keylen is out of range. So this error is both slightly unhelpful, like the error is that the number is not an integer, not that it's out of range. But it's also crashing a program that previously worked. So when you're adding errors to a library later in its life, think about, should that error get to crash all the programs that are currently using it? Is there a better way you could communicate that failure to the user? For example, it's quite common for people to dig around in the console and look at the properties things have to figure out how to use them. One convention that we have in JavaScript is that if you're accessing a lot of things with underscores, that's a signal that you're doing something private that the author didn't intend for you to rely on. That's not something the language enforces for you, but it's a way that you can signal to the user, like, hey, I didn't mean for you to use this, and it will probably break later. And the final thing that we have to rely on is documentation. So documentation should help people use the code in the way that you intended. Often people land on Google, and even if you have really good documentation, arriving at prose that requires a lot of context will usually give people more questions than they arrived with. Like if I arrive at this bit of documentation, I might be going, oh, what's a driver object? Should the URL be an object or a string? How do I connect this stuff together? It's really helpful to just give people a self-contained concrete example that they can get running locally, and once they understand the basic concepts, then they're more ready to dive into your API details and understand things in more detail. And finally, we have testing. So testing is a huge topic that I cannot possibly cover in like the minute that I have remaining, but one thing that I often see people advise with testing is that you shouldn't test your dependencies. Don't test third-party code. That's actually a really good idea. You can do that because what it does is it validates your assumptions and it tells you when they're no longer true. Like I could write a method, like me as the user of the contains function we saw earlier, I could write a test that says, oh, it works with sets. And then one day that will, when the author changes it, that test will stop working. I'll get an error, and then I'll immediately know that the reason half my application is failing is because this one assumption that I had in my dependency is no longer true. So what have we learned? So we've learned that compatibility is not purely a function of the source code we're looking at. It's determined by the context in which it's used. We've learned that that context is constructed by how people use your program, something that you very often don't have any control over. And finally, that you can influence that context by how you communicate with the users and how you tell them how the software is supposed to be used. Thank you very much.